All right, welcome to the second video that finishes up chapter 10 for us. And now we're going to talk about some of the macroscopic effects of intermolecular forces. And so one of them is the fact that, well, if you happen to be a bug called a water strider, they're not very big, you can, if you are so inclined, walk on water. Now note that you can almost see that there is an impression where our bug here is actually on making contact with the water, but it just seems to not be enough to break through, so the bug doesn't fall through. And for substances like water that have very strong intermolecular forces, it turns out that you might think that, yeah, this is a bug, they're not very heavy. But you can also do this with much more dense substances like steel. So if you do this just right, you can actually get a solid steel needle to float on water. And this is due to something called surface tension. And the idea is that for some reason, this object just can't break through the surface of the water. So why would that be? And I will go here to a molecular level cartoon and kind of explain. So imagine these are water molecules, and they have some attractive intermolecular forces, the hydrogen bonding, to their neighbors. And let's say you were our needle, or the bug, and you are placed on top of there. Well, yes, gravity is pulling you down. But for gravity to pull you down, you actually have to break through the water molecules. Basically, they have to get pushed out of the way. If these intermolecular forces, these attractive intermolecular forces, are stronger than the force of gravity pulling the object down, then this object will not break through this first layer and float. So basically, the attractive interactions between these water molecules on the surface and their neighbors sort of form like a skin on there. And the stronger these intermolecular forces, the greater the surface tension is. So for example, that needle trick would not work with a substance that had a much lower surface tension or much smaller intermolecular forces, like, let's say, hexane or something like that. So it kind of needs to be water. All right. And another thing I want to talk about is, again, while this graphic is up here, is the fact that there is a difference between the water molecules that are on the surface and the ones that are sort of in the middle. So the ones that are in the middle have attractive interactions to their neighbors, but the neighbors are in all direction. So the result is that this molecule is not being pulled in any one particular direction, because it's being pulled in a bunch of directions, but equally so, and everything cancels out. That's not the same for any of these water molecules that are on the surface. Because they don't have any neighbors above them, there is a net pull of this one into the middle. Now, this has a couple of ramifications. The one thing, I guess the way I like to think about it is that because this one, the ones in the middle of there, have a lot of attractive interactions, more so than the ones at the edge do. These are lower energy than these are. Mother Nature is a lazy slob, so Mother Nature also wants to minimize the number of surface molecules and maximize the number of interior water molecules. And this also has an important effect. Beating. So the relative intermolecular forces for two substances at an interface is called adhesion or cohesion. And so this is water on glass, except one side of this glass slide has a wax coating on it and the other one doesn't. And I'll give you a moment to figure out perhaps which one is which. All right, and hopefully you got this. So this side is the part that is just glass, and this side is the part that is not glass. Now, what you need to know about glass is that it is, a bunch of silicon-oxygen bonds. It is very polar. So polar glass and polar water get along really well. So in this case, the water adopts a shape that maximizes the contact area between the two. So they're spread out, but wax is very nonpolar. So the water molecules would rather interact with themselves than the nonpolar water molecules. So in this case, they actually end up adopting a shape that maximizes the interactions that the water molecule has with themselves and minimizes their contact with the wax. So they form little spheres. And so the sphere has the maximum contact area of the water with itself and minimizes the area where the water is actually touching the wax. So again, the water energetically is better off dealing with itself than with the wax. Mother Nature's lazy. So water beads on waxy surfaces and it spreads out over regular glass. And this, by the way, if you wondered about it, is why aqueous solutions form menisci in glass test tubes or cylinders or whatever. So again, this is a kind of a molecular picture of glass. It's the silicon-oxygen bonds are very polar. The water molecules are quite happy to interact with them. So basically, energetically, it's worthwhile for them to overcome gravity and creep up the side so that as many of them as possible, as many water molecules as possible, interact with the silicon. And so that's why the menisci of water in glass looks the way that it does. Now, could you make it go the opposite direction? Yes, you could. So water is very polar, gets along with the polar glass. Liquid mercury, for example, is not polar at all and would rather not interact with the very polar sides of the glass. So mercury actually has a meniscus that is the opposite. So the mercury atoms, in this case, would rather work a little bit to overcome gravity, and rather than fill in this edge right here, go up a little bit higher than they otherwise would to interact with each other. And so this is concave down, and the meniscus here is actually going concave up. So in this case, the mercury would rather cohere to itself than adhere to the polar glass surface. And so these are all manifestations of the fact that the intermolecular forces, again, so you've got strong dipole-dipole interactions here, and you don't really have anything going on here. All right. And one more thing to go over, and that's viscosity. So this is another thing that is a hallmark of the intermolecular forces. The definition, it is a resistance of liquid to flow. On a molecular scale, it tells you how easily the molecules in a liquid can get out of each other's way, because that's how stuff pours. The stronger the intermolecular forces, the less likely they are to get out of each other's way. And that is referred to as a high viscosity. So something with high viscosity does not pour particularly easy. So gasoline has a very low viscosity, molasses a very high viscosity. So stronger intermolecular forces result in something with a high viscosity. I should note also that the nature of the intermolecular forces is not the only thing that goes into that affects the viscosity. Temperature also does as well. The higher the temperature, the more easily something can get away with each other. So increasing the temperature of a particular compound will lower its viscosity. So molasses are a bit easier to pour in June than they are in January because it's typically warmer. And that's it for the macroscopic manifestation of intermolecular forces.